This is Honors Algebra 2 Pre-Calc. We're doing section 9.4 in Pre-Calculus, which is mathematical induction. So we're going to go ahead and do example 3, which is we're going to prove the statement 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared equals n times n plus 1 times 2n plus 1 all over 6. Cool. So we're going to go ahead and prove this by induction. So we're going to do the same two quick first steps that we've been doing, and I'm going to inch over here to do them because I'm going to need some room for this proof. So step number 1 is to show that P sub 1 is true, right? You have to do this step every single time. So P sub 1 on the left-hand side is just going to be the first term, 1 squared. And the question is, question mark, does that equal what happens when I plug in a 1 for n? So 1 times 1 plus 1 times 2 plus 1 all over 6. So I get a 1 equals, and then when I clean this up, I end up getting a 1 times 2 times 3, which is a 6 over 6. Sure enough, 1 equals 1, check, P sub 1 works. The second thing I have to do is I have to assume that P sub k is true, right? I'm going to assume that P sub k is true, meaning 1 squared plus 2 squared plus dot 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 up to k squared is equal to k times k plus 1 times 2k plus 1 all over 6, okay? So those are the two steps you have to do before you can get really to the meat of this mathematical induction, which is going to be a lot of work. My third step, which I'm going to end up finishing up here, is going to be to prove that P sub k plus 1 is true. So now, using this information, I'm going to prove or show that P sub k plus 1 works. Again, what we're showing is that P sub k plus 1 works if P sub k is true. So we're saying that P sub k implies P sub k plus 1. So P sub k working will lead to a domino effect where the term after it will also work, and that's true to infinity. So that's what we're going to do up here is we're going to prove P sub k plus 1. So that's step 3 where we prove that P sub k plus 1 is true, okay? So the way we're going to prove that is we're going to write the P sub k plus 1th term on each side. So on the left-hand side, we're going to get a 1 squared plus a 2 squared plus a dot 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 up to k squared, which I specifically stop at for a sec because I have an expression down here that talks about going up to k squared, plus the one term that makes it different than the kth term, which is the k plus 1th term. And I'm trying to show, with a question mark, that that's equal to what happens when instead of plugging in a k for these n values, I plug in a k plus 1. So instead of plugging a k for n, I'm going to plug k plus 1, which means that when I plug into the second term, it's k plus 1 plus 1. And when I plug into the third term, it's a 2 times the parentheses k plus 1 plus a 1, all over a 6. So I'm trying to show that this left-hand side equals this right-hand side. So there are two things that I need to do before moving forward, right? The first thing is it's going to really benefit me a lot to go ahead and simplify this right-hand side a little and take things like a k plus 1 plus 1 and turn it into a k plus 2. So instead of leaving this as k plus 1 plus 1, I'm going to want to make this a k plus 2. And instead of leaving this as a 2 times the quantity k plus 1 plus a 1, I'm going to make this a 2k plus a 2 plus a 1, which would make this whole thing a 2k plus 3. So that's going to make your life a lot easier if you clean up that numerator. So I'm going to end up wanting my right-hand side to look like a k, or rather, I'm going to have my right-hand side look like a k plus 1 times a k plus 2 times a 2k plus 3 all over a 6. And this is what it's going to be my goal to make the left-hand side look like. That's what I'm aiming for, is to make this left-hand side look like that. So now let's go ahead and do that. So the first step, and I'm going to erase some of the stuff I have over here because we are going to need the space in this problem, is that in my step 2, I realized that I could assume, in fact I had to assume, that P sub k, this whole thing was P sub k. So this is P sub k, and we've assumed that P sub k could be written as k times k plus 1 times 2k plus 1 all over 6, right? And the only term that's left out of that on the left-hand side is the k plus 1th term, because this was P sub k, meaning all the terms up to k. So now I need to make this thing look more like this. Now there's a couple ways that I can do that. It's entirely up to you. I would say that it is not a great idea to FOIL everything out, and here's the reason I say that. If you FOIL everything out, you're going to have to factor with synthetic division. It's going to be awful. What I notice is that there's a k sub 1, or there's a k plus 1 GCF on this side that I could take out, and there's going to be a k plus 1 on this side. So it's going to behoove me to leave that k plus 1 as it is. So I'm going to go ahead and start by timesing this thing by 6 over 6 to get a common denominator. So now what it looks like I have on the top is my first term is a k times a k plus 1 times a 2k plus 1 plus a 6 times a k plus 1 quantity squared all over a 6, right? And again, I'm aiming for this thing at the end. I'm just going to keep simplifying on this side. I notice that there is a GCF of a single k plus 1. I also notice that that k plus 1 exists on the right-hand side, so if I yank that k plus 1 out, it's probably not going to be bad for me. When I take that GCF out, what's left is a k times this 2k plus 1 plus a 6 times the only other k plus 1 that was left, okay? Now, if I clean that thing up, I already have the 6. I already have the k plus 1. I would wager that if I clean this thing up, it's going to factor into a k plus 2 times a 2k plus 3, and that's exactly what's going to happen. So, but again, I'm low on space, so what's going to happen is I'm going to come up to the top, and I'm going to buy myself some space, okay? So, we'll loop back up to the top. So if I go ahead and clean up my left-hand side a little bit, I have that this is a k plus 1. Now, when I clean up this, I get a 2k squared plus a k. So I get 2k squared plus a k plus a 6k plus a 1 all over 6. And again, I'm trying to show that that's equal to a k plus 1 times a k plus 2 times a 2k plus 3 all over a 6. So again, I just want you to notice that as you're going, I see that I already have the k plus 1 over 6 and the k plus 1 over 6. It's a fairly reasonable bet that this whole thing is going to factor into these two factors that I want, right? Okay. So, buying myself a little more space. So sure enough, I have this k plus 1 times a 2k squared plus 7k plus 1. Oh, it's not a plus 1, it's plus 6, mea culpa. Plus 6, my bad. Sorry, guys. All over a 6, right? And I'm trying to show that that's equal to a k plus 1 times a k plus 2 times a 2k plus 3 all over 6. So I look at this, and even if I didn't know what it factored into, I'll be honest, the smartest thing you can do is say, well, I've got this, and this, and this, and this, so this piece is probably this, and you could even FOIL in your head to check and see if this pans out to be this, and it absolutely does. So you're going to get a k plus 1 times a k plus 2 times a 2k plus 3 all over 6, and that's equal to a k plus 1 times a k plus 2 times a 2k plus 3 all over 6. So QED, you have proven that. So essentially, again, the way to think about proofs by induction, so you've proven this P sub n, which is that the 1 plus, like 1 squared plus 2 squared plus 3 squared, da 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 da, plus n squared equals an n times an n plus 1 times a 2n plus 1 all over 6. But again, the way to think about mathematical induction is sort of like dominoes, okay? By proving P sub 1, you've shown that the first domino exists, right? And then you assume that if some arbitrary domino, P sub k, the kth domino down the line, if that domino works, then it implies that the domino after it, k plus 1, will also work. Well, now, once you've shown that if k works, k plus 1 works, well, now go back to what you've shown. You showed 1 works. Well, based on the other thing you proved, if 1 works, 2 works. Well, based on the other thing you proved, if 2 works, 3 works. Based on the other thing you proved, if 3 works, 4 works. And you could do this forever to infinity, but you won't because that would be miserable. That's why we do proofs by induction.